So I'm going to talk today about a way to use routers for things that are not specifically link-oriented. Who owns a router? Raise your hands. What the hell? Not even Linksys? Bixby. So if you own a router, you happen to own a load balancer, as I discovered. What's the point of us using a router for a load balancer? In my mind, the point is quite narrow. It's for a collection of services that really don't have a whole lot of value. And that is, well, they have value, but they're not going to have a value in the sort of scale that you might see at Yahoo or at Google, or at folks who do 300 machines behind an address, that kind of stuff. Kind of the idea here is that we want local load balancing sometimes. For instance, things that have really wonky behavior, such as resolver client libraries in Windows or Unix boxes. We also want to use just the simplest things possible. I like the router, I already have it. Why add another piece of gear to affect load balancing? So my concept for this generalized fast server load balancing is simple. Utilize existing structures or features within hardware, like ECMP in this case, to affect the same types of connection load balancing behaviors as you see in more stateful, more aware, more costly devices. The other important point to mention is that if we do this in a router, we benefit by all the work gone into the forwarding path. I can't think of a single 10 gig layer 3 box that's not 10 gigs at layer 3. If it can do that, why not use it for distributing traffic to machines? Links are good, but we can do this with machines too, I discovered. So what are the ingredients for this? Generalized fast server load balancing needs a couple things to work really well. On iOS is where I basically implemented all of these things, or this process, and it needs three things. It needs response time reporters, things to do health checks. This is sometimes called IPSLA. The second thing we need is an enhanced tracking feature. Tracking objects were around for a long time to make sure one interface could follow another interface's state. For example, taking down one port if any in a link ad group went down, for instance. This now can track other things like IPSLA objects in iOS. So the configuration involves those two things. Both of those are the underpinnings for the ECMP to work well. Once you do all these things, you affect this generalized fast server load balancing concept. Why is this good for us? If we can use a router to affect server load balancing and do it in a very simplistic manner with the previously mentioned things, the track and the response time reporters, we don't have to run OSPF or BGP or whatever it was we were doing to our end hosts, which I've heard a lot about from a lot of people. That's not a bad concept, but it seems like a lot of extra work. It also seems as if in many locations or many circumstances you won't be able to run a routing protocol to the device you wish to load balance the service to. So it's kind of a non-start in some ways, and I think I can remove that with these mechanisms. Another good point about this concept is that it's all routing. There's no state on this stuff. When the packet comes in, the header is used to create the hash. The source and destination IP addresses in Cisco's ECMP case minimally affect the selection of the next hop. This is a far cry from things that know about source and dest ports, things that know about the nature of the URL. And in our case, we're not going to be concerned with those things. So strip them away, use the router. How does it look? Effectively, we have just two pieces. The normal router you always had, and for the sake of the example, we're using 10net. In this case, we have three machines we care about, and we want to say that we'd like to have them all handle the same load for a common address. Let's call it, you'll see later on, we'll have that ECMP to these three machines. In this case, what we're doing is called direct server return, where each machine's target service address is living on a loopback, not on the Ethernet interface in that /29 in that access VLAN. The return traffic is next hopped to 10.0.0.1. In this example, we have this interface, VLAN 100 again. Direct server return does the right thing from .0 and .3 up to .2 and .3. And we basically, in this configuration here, would have these enumerated with similar addressing as I'll show you here. So text config again, VLAN interface, you always have that. Response time reporters, this is kind of a simple example, just two of them. We're doing our scenario based on a recursive name server pair. I like the fact that the resolver libraries will try the first and fail to the second, but I don't like the fact that they never try the second to begin with. This is an example of a really silly really silly workload created by resolver libraries. I'd rather have both machines take some of the load. Why not? I'm paying for the power. I would also prefer that if one of them failed, I wouldn't have to tell anybody about that and wouldn't have to have customers becoming enraged or angry that they're waiting for a timeout to get to the second server. If we have these response time reporters checking .2 and .3, the actual servers here, if one goes down, our following config will track that. We have track 1 and track 2, tracking response time reporter 1 and response time reporter 2. Now, why is that useful? It's useful up to this right in this part here. Standard ECMP routes are configured manually. You'll note one additional element at the end of the route, not a metric or anything else or a tag, but in this case a track option. We're saying that for the destination .2 and .3, that we have two possible next hops, 10.10.10.1, 10.10.10.2, whatever. I'm sorry, for the destination address there, the next hops are 2 and 3. For that particular host, we have two candidate routes. You'll see 10.10.10.1, 10.10.10 goes to .0 and .2 and .3 alike, and 10.10.10.2 goes to 3 and 2 alike. With track 1 failing, those routes would be expired. We'd have all the load to the remaining machine. The same is true for track 2. How's it look under the hood? If you do a show IPsef internal for that particular next hop, for any of them, you'll see the 16 hash buckets alternately have themselves pointed to .2 and .3. In the case of the even numbers of routes, this works just fine. A problem that Cisco's always had, or seems to have had for a long time, was uneven distribution of which hash bucket points to what next hop. In current code, my observations are that you actually do see Ceph resize things or recarve things into odd numbers of buckets. In this case, with 3 valid next hops, 2, 3, and 4, it truncates the 15th bucket. Kind of cool, finally. So some examples of doing this. Here's a quick test we did. 2 name servers up, pointing queries towards NS1, pseudo-random sources, just a stupid little script running through, and we see about 10% equivalence of the load balance. So, yeah, it works. Who'd have thought? Some caveats, obviously. Today, ECMP in Cisco is 16 paths maximally. This can be resolved by having 2 switches. We've done some chaining, if you will, where one switch has 2 next hops living in a second switch. Each of those machines, each of those next hops then, for machine A and machine B, if you will, can have multiple more parallel ECMP routes. So if you were to go totally hog wild, I would presume you could do 16th to the 16th possible machines behind this concept with 2 switches. I wouldn't maybe recommend it. Maybe a server iron's good then, but it certainly is something you might already have in the rack, so why not? Connection tracking doesn't really exist. If a machine were to fail from the group, say a 3-machine group failing to a 2-machine group, any distribution you'd have of connections aren't guaranteed to be sustained to the machine they were currently going to. Because the hash buckets are going to be recarved completely, a session that was coming in towards NS1 or a TCP connection to www1 may now land on 2 if the third fails. That's an issue, but be aware of it. You also don't have the ability to let the protocol, in this case ECMP is not really a protocol, but the mechanism doesn't know at the load of the underlying machines. For an application like recursive name server purposes, irrelevant. For something a bit more complicated, web interface or some ERP stuff where a query could take 10 seconds or a minute, might be a bigger problem for you. Don't do this. Do something a bit more elegant. We also don't get any support in these kinds of products for direct, easy ways to translate, say, a public IP on a virtual interface to an arbitrary number of 10 dot something machines behind it. If you wanted to use NAT features, I guess 720, 3BXL, whatever, can do this translation. You're going to have flow overhead for connection setup and teardown. Just deal with that. Interestingly, in this research, we discovered that on SX and SR and newer versions of 12.4T, there is an option to include in Cisco ECMP calculations layer 4 headers, layer 4 portions of the header. And it seems to be an even more even distribution when using that. So in summary, a couple things to keep in mind. Just configure it. Do something and show IP profit. Thanks. One minute.
And if Leo's already on his way up, great. And after Leo, it's Brian Dixon.